I used to run a skin fade.
Okay, guys, lab this week is a continuation of last week. You'll have half the lab, and we'll go downstairs and have a lab lecture. Okay? We'll take a look at probably IR, see what type of questions come up on IR, and other things as we have time. You'll have about an hour to maybe an hour and 15 minutes to finish up the lab portion. Okay? We seem to be in reasonable shape. If anybody would like to come by this morning after class between 9 and 12 and do like an IR or melting point, I'll allow you to do that. Anybody like to do that? Okay. You can also let me know after class. Today between 9 and 12 if you like. Okay, I'll open up the IR room. We'll have a quiz on Friday. Okay. Over material since our last quiz. Test is next Wednesday. Is that right?
Yes.
Anything else to mention? Yes.
Did you say the quiz on Friday is going to be open? The quiz on Friday?
Material since the last quiz. Yes.
Is that going to include IR?
Should it include IR? You think? Yes or no? I think it should include IR. IR will be on the test, so we need to make sure we're making progress on IR. Other questions? Yes?
Are you still planning to do a review session on Monday?
You want to do one this Friday? What's today, already Wednesday? Friday at 7:30? I'll do this. The class is empty after Friday. After this on Friday, I'll do 7:30 to 8, and then I'll also do 9 to 9:30. Anybody 9 to 9:30 okay? Okay, 30 minutes before and 30 minutes after on this Friday. Anything else, guys? Okay, 8 o'clock is go time, guys. Okay? All right, I think the curtain is pulled back and it's time to go. Dress rehearsal comes before 8 o'clock. Everybody good? Okay. Confirmations. Confirmations. Any questions about anything while this is warming up? Confirmations. Okay, like butane. We'll look at the handout. We have a purple and then we have a white set, yeah? Okay, we got lots of sigma bonds. This thing can rotate, yeah? This is butane, 4 carbons, 2 H's, 2 H's. These are carbons on the end. We can draw this on the board with a Newman projection, circle, circle, dot, dot. Need to know how to do that. Need to know various things, dihedral angles, etc. Sometimes called torsional angles. Rotation. This central bond we can rotate. This methyl compared to that one over there. I'll turn them both up. What do you want to call it? This is a conformation. Sometimes called rotamers. Different conformations, okay? I can be standing out like this. I can be standing out like this. Okay? I'm connected here. I just have different conformations. Okay? What do you want to call this conformation? I can't see the other one behind the front one.
Center cis.
It could be called center cis, or more broadly termed would be eclipsed. Okay? Sun in front of the moon, or the opposite. Okay, what if I turn this a little bit to a 60-degree turn? That's the most common turn, okay? I could do a million turns. I could go boop, 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 million, okay? Typically we turn 60 degrees at a time. And that's, if I do that, I go from here to there. No, that's more than 60. No, that would be 90. That's a 90-degree dihedral angle. 60 would be there. No longer eclipsed. Okay? That's staggered. Staggered. Okay? And we see these in the top diagram here. Now that is ethane, two carbons with all these H's on the end in this model. Okay, let's do it here. H's, this H is eclipsed with the back one. And we're starting there. We turn this. Now it does start. And it goes down. Okay? Are they turning the front or the back? Turn the back. Let's turn the back. The back is rotating. See, as we rotate it, why is this high in energy? Because it's eclipsed. Eclipsed is always highest in energy because they're the closest. When I turn this, they're going to spread out a little bit. Highest in energy. And we're going to rotate 180 degrees around here. Okay, we're turning the back. Bam. And we come down to here. This is the best because then we're going to go back uphill. This is the best because it's staggered. Okay? If you look through there, if this is an H straight up, there's not one over here straight up. It's called staggered. There's different terminology here. This is broad terminology. We keep turning the back and we get back to up, 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 up. Why is it high now?
Eclipse.
Because it's back to eclipse. Keep turning. Should be here. Yeah, right? Front carbon, the H is straight up. Back carbon, straight down, H. See? That's there. But see, that is no different than this. And that right there is no different than that because an H is an H is an H. So we go back and forth between really only two conformations here. Two energy levels, and it just cycles back and forth. I'll go all the way through one time, back, rotating the back. Eclipsed, 60-degree turn, staggered. 60-degree turn, back up, eclipsed. 60-degree turn, back down, staggered. 60-degree turn, back up, eclipsed. 60-degree turn, back down, staggered. And 60-degree turn, back up to eclipsed. And that is exactly where we started. In the end, there's only two discrete energy levels because each time you go, because every eclipse is the same. Because an H is an H is an H. If we label the H's A, B, and C, they might be different, but in real life, H's aren't labeled with A, B, and C. An H is an H. You can understand the energy diagram. There's two repeating conformations. One's called eclipse, one's called staggered. Staggered is always better than eclipsed. Eclipsed is high energy because they're right here lined up with each other. Why is it high energy? Because the electrons, bonds and molecules, the outer skin is electrons. Okay? These electrons are, I don't like being eclipsed. And when we move staggered, it's much better. Question?
If you said that because it's all hydrogen, so it's the same conformation. And so the eclipse will have the same amount of potential. But if it's a methyl group or two methyl groups.
Right, and below it will be different.
Okay.
Let's look at below. Below we have more than two. We have 1, 2, 3, 4. And then it's a repeat. Now here I'll use this model, and that's now a methyl here and two little H's there. We start down here, we have other terminology. Let's start with the methyls being eclipsed. Okay? That's that there. Dihedral angle 0 degrees. If I turn that right there, the dihedral angle is now what? 90. 0 degrees. Eclipsed. We can use that same terminology. That is the highest energy there, A. We're rotating the front carbon here. Do you see that? Front carbon is being rotated here. Let's do 60 degrees. We get to there. Methyls are now have a 60-degree dihedral angle. This is called gauche, or to the side. I think that's French. That is a type of staggered. Gauche is a type of staggered. It's lower in energy because it's staggered. Staggered is always better than eclipsed. We do another 60 degrees, and it comes here. This is eclipsed, but it's not the two methyls eclipsing. It's the H in the methyl eclipsing. And because the H is much smaller, it's not as bad as over here with the two methyls were eclipsing. So we get to here. Now it is eclipsed, so it's not as good as staggered. But this eclipse is not as bad as this eclipse. This is like total eclipse. We would also call this the two methyls are syn to each other. Syn. Here the H and the methyl are syn or eclipsed. The methyls are, well, you wouldn't really call that gauche. Gauche is 60 degrees. Okay, we keep turning and we get to, bam, the front here. Now the methyls are totally opposite. That's called anti. Where this over here was called syn. Anti. Anti is a staggered. I mean, you can see it here better if you can understand the Newman. It's okay. But this staggered is better than this staggered. Anti is better than gauche. Because even though they're to the side of each other, they're still kind of close. That's bad. That's better. This is best. Anti. Much more room. Now we start repeating. We just did a 180 degree turn. Keep repeating and we get to the H and the methyl are eclipsed. But that was like back over here. And I wish they would label this a C again. I wish they had gone A, B, C, D and then call this C. Write C under here. I think that's going to be right. C under there, B under here, and then you're back to the original. Because F and B are the same. It doesn't matter if the two methyls are gauche on that side or this side. And then we rotate the methyl back up to eclipse, and it's back over there. Anti is the best, lowest energy. The two Bs are the next best because they are staggered. The two Cs are next because they're eclipsed. Hopefully I said the right word earlier. But C is not as bad as A. A is like total eclipse or syn. I reckon we can call C partial eclipse. I don't know that you see that in the textbook. Two biggest groups eclipsed versus one group being smaller. Okay, you need to understand that in the terminology used there, staggered is always better than eclipse. So there's actually 4 different energy levels down below. That was the question, yeah? Is that what you were referring to? Okay, let's draw conformations. Purple. And most of that has been discussed. Okay. Everything up there we've discussed at some point. Let's start doing some drawing here. Draw this compound in the most stable conformation, looking down the 1,2 bond. Okay, 1,2 would be from nomenclature. Okay. What's the name of that compound real quick? How we doing on nomenclature? One chloro, one. Chloro. Yeah? How's it look? How's it look? Good? Okay, I think it's good, yeah? Somebody seemed to say something different. Somebody say 2? Y'all seem troubled by the thing. No? Good. 1-2 bond, okay? This is 1, this is 2. Looking down the 1-2 bond, so we will stand over here, okay, and we want to look through there. That's a little man there. Okay? Front carbon is here, 2 in the back. 1, 2. I'm looking down the 1-2 bond. Okay? What do we see on carbon 1? I see the 2 halogens. Okay, what do I see? Circle, circle, dot, dot. Front carbon, what do you see? I see a fluorine going straight down. Fluoro. U-O. Fluoro. I see a chlorine. Is a chlorine to my right or left?
Left.
Okay. Chlorine to the left. And what is also on the front carbon? I'm drawing H. When we draw Newman conformations, we do draw in the H's. Front carbon, yeah? Okay. That right there, I think half of you would get wrong. So, everybody good with that though? Okay. Back carbon, what do you see?
Well, just all it.
What's on the back carbon?
All 3 H's.
2 H's, 1
2 H's.
We'll put an ethyl there. Going straight up, yeah? Mhm. Fluorine is, okay, we'll make chlorine green. There it is on the board. Everything's in the plane. The F is coming over here, blue. Chlorine is bold or dash. It's dash, which means it's going back. See how the green is going away from you? That's back. Okay? Here it is on the board. What do I see? Okay? You want to see what I see? That's what I see. Okay? I drew it on the board. What's on the front carbon? I got an F straight down, blue. I got a chlorine to the left, going up. See the little H going that way? What's in the back there, on that carbon? 2 carbons, going straight up. Okay? Yes, it has free rotation. I can rotate that many ways. We rotated it in the energy diagram. That's how it's drawn on the board. That's what I'm looking at. I see 1 and 2. How did I get here? Again. There we go. I stood over here. It's on the board. I stood over here and said, hey, I see a fluorine straight down. Everybody, if you're right here, do you see a fluorine straight down? Well, that's what I drew. I'm drawing what I see. I see a chlorine to my left. I drew it. That's why I drew it on the left. Okay, that's as drawn. Question, is that the best conformation? And the answer is no, because the best conformation is going to be the one in which your largest groups are anti. Okay? Anti is the maximum spacing. The largest groups prefer anti. What's the largest group on the front carbon? Chlorine. Okay? As the halogen gets bigger, we say it's bigger. What's the biggest thing on the back? By the way, we didn't draw in the H's on the back. Okay, carbon 2 has 2 H's. We should draw in H's with Newmans.
Are there two up top, two H's?
Here?
Yeah, somewhere, because there was two more like poking out.
Well, there's 2 there and there's 3 here. Don't need to draw, just need to draw them around the circle, circle, dot, dot. What's the biggest group on the back carbon? Alpha. What's the positioning of the 2 largest groups right now?
Go.
What's the
Staggered.
They're staggered, but there's a, yes, a gouge. Right now, these 2 groups are gouge. Okay, is that the best? No, we want to rotate this, okay? We want to rotate this. We can rotate the back or the front. It doesn't matter. I'm going to rotate the front because I'm holding the back. I want to rotate this, put the chlorine anti to the ethyl. I'll do it on the board. I'm just going to rotate this. This is me rotating. And now we have, the back is the same. Ethyl, H, H. Now the chlorine straight down. We're just taking this front and turning it. Chlorine comes here, chlorine goes there, H goes here. And there's the best, because the 2 biggest groups, the ethyl and the chlorine, are anti. And there's your answer. Now we can have questions. In the best conformation, what is the positioning of the ethyl and the fluorine? Yeah. In the best conformation, the ethyl and F are gouge. We see that, right? Okay. What's the dihedral angle between the ethyl and the H in the best conformation? The ethyl and the H. There's only one H that's possible to have a dihedral angle.
60 degrees.
It's 60 degrees. The angle, what's the angle between the ethyl and the other H's?
120.
120.
109.
109.5. Right? This H and that ethyl, dihedral angle. This H in the ethyl, that's just a tetrahedral carbon with 109.5. There you go. Okay, we'll do the other one real quick. The next one. Looking down the 2-3 bond. Nomenclature. This is 2, right? That's 3. I'm going to stand over here. Looking through there. I'll make up a question so we can get there. In the best conformation, what's the relationship between the bromine and the methyl?
180 degrees.
Do what?
Anti.
The bromine and the methyl? I'm thinking that's not right.
Oh.
Okay, front carbon, what do we see?
Bromine to the right.
I see, what's coming straight down to my feet?
Methyl.
Methyl. I like to put an ME here just to clarify because it's just sort of a line. If it was longer, it would be more clear. That's the methyl group on carbon 2. We're looking down 2, 3. Carbon 2 has a methyl this way. What else does it have? Bromine. Okay, if I'm over here, is the bromine on my left or right?
Right.
Coming off the board. If I'm over here, off the board is to my right. It's bolded. It's coming towards you guys. If I'm over here, you guys are to my right. Okay? It's also going up a little bit, up and right. Bromine. What's going back on carbon 2? Because 2 is tetrahedral. 2 in the plane, 1 forward, 1 back. What's going back on carbon 2? And I draw an H, but we're going to draw it in the Newman. There's the front carbon. Back carbon. Carbon 3. What's in the plane going up or down? Ethyl. And the ethyl is straight down. Uh-oh. The ethyl is what to the methyl? Those are actually eclipsed as drawn. So I'm drawing a little bit skewed, but it's implied that it's a 0 degree dihedral angle. What's on carbon 3? There's a methyl there. Okay. That's a bond to another carbon. It's just showing stereochemistry. It's dashed means that bond, that methyl is going back. If I'm over here, the methyl is on my left. Okay? It's eclipsed with the H. What else is on carbon 3 coming forward? Undrawn H. It's eclipsed with the bromine. Is that the best confirmation?
No.
No. As drawn, that is not the best. You would commonly draw that however you want. Now we're doing a finer assessment. What's the biggest group on the front?
Bromine.
It could be a little unclear. Is it bromine or methyl? I'll try to make it very clear on a quiz or test. Okay. Halogens. Bromine's bigger than chlorine. Iodine's bigger than bromine. Alkyl groups. Which is bigger, ethyl or methyl? Which is bigger, propyl or ethyl? Okay, so as it gets bigger, it's bigger. When you start comparing apples and oranges, it can be a little tough. You may have to look up values, because steric values have been determined. But we're not going to go there. Front carbon, I would say bromine. Back carbon was what? Methyl, ethyl, or H?
Ethyl.
Yeah. We need to rotate this. You can rotate front or back. It does not matter. Which do you want to rotate? I'll rotate the front. That means let's leave the back the same. The back has what? H. Don't get confused because up here, one H is on the back and one H is on the front. Back, methyl here. And the back is what? Ethyl. We're going to rotate the front. We want the bromine to be anti to the ethyl, right? So we just want to rotate this a little bit. The bromine is going to go straight up from the front. Okay? The H comes here. And what else is on the front? Methyl. There you go. That's the best confirmation because the bromine and the ethyl are anti. And for us, that's it. Biggest group's anti. What was my original question? What's the relationship between the bromine and the methyl?
Methyl.
And methyl? So what is it?
No. Yeah.
Which methyl? I got two methyls. I'm referring to the one in the back because that one is always 109.5 no matter what you do. They're on the same carbon. Yes. Bromine and methyl or gauche and the best confirmation. Yeah? What's the dihedral angle between the two H's in the best confirmation? 180, yes. So now we have terminology that we can discuss. And which is easier to see answer these questions I'm giving you, the original or the Newman? Newman, right? That's why Newman became famous. He developed this circle, circle, dot, dot method. Wow, that's an easier way to look at it. Thanks, Dr. Newman. Made my life easier. Harder to look at this. But this, you've more commonly seen it drawn like this. Somebody says, show me a compound. Nobody's going to draw you a Newman unless they have to. We'll see more. There's one you can do on your own. We need to move ahead. Questions? Can center gauge conformation sometimes be preferred over anti? Yes. This compound here, very simple. It actually prefers the OHs, which are the largest groups, not anti, but gauge. Why? Thank you. One more time. All right. That's good. I like it. Can we illustrate that with a NCI? What's that? Non-covalent interaction. How about this right here? Does that look like a hydrogen bonding NCI illustrating between the oxygen lone pair and the H that is on an O and interrupt? That hydrogen bond is like a little glue. Okay? Pretend these are two OHs in my hand. Anti. Actually, no. Little glue here, hydrogen bond, hold it up like that. Okay. So when it's hanging out on a Saturday afternoon, instead of these OHs being like this most of the time, again, molecules don't just sit there, but they have some vibration. Is it going to be, this ain't it, but is it going to be more like this, these two groups here, or is it going to be more like up in here? It's going to be more like up in there because there's some stickiness up there. Okay? That NCI, or IMF, whatever you want to call it. Okay? So the answer is yes. There's an example. Is intramolecular H bonding possible in the following compounding? What is intra? Well, that was intramolecular right there. Internal, within the same molecule. How about down below? We're not going to do a Newman here, but since we mentioned hydrogen bonding, just want to make sure that we can do this. Can that H hydrogen bond with anything?
No.
Yeah. Can it reach? Can this bond rotate? Yes, that's a signal bond. What if we redraw this? We're going to rotate that. Okay. OH down. Thumb. Here's the bond. Rotate it. Now OH up. All right. Now, look what we can do. Nice little NCI there, hydrogen bonding. And that is illustrating an intramolecular H bond. Also in this example, I didn't have to use a Newman. I think I put this question here at some point because after showing the first one, then I had students like, well, I need to draw in a Newman. No, you don't have to. We did it right there. There's no Newman there. It's still showing an intramolecular H bond, and it's illustrating the fact that you got free rotation, so these groups can rotate. Just like my shoulder, if I want to slap hands up here, my shoulder will allow my hand to move up here and do something. It's not fixed, right? That's a rotatable bond. All right? You need to be able to go the other way with Newmans. Can you give a name for these compounds? Let's do this real quick. Now, it all depends on if you want to keep the stereochemistry. I got two carbons, front and the back, right? Here we go. There's two carbons. What's on the front carbon? How about this? I see a methyl. If I'm looking at this straight on, front carbon, straight up is a methyl. Everybody agree?
Yes.
So if I'm over here, straight up is a board. And it's a methyl, not so long. Looking at it, what's on front carbon to my right? Bromine. front carbon to the right. I'm over here, because this is front carbon, that's back carbon. AB. Should I draw the bromine bolded or dashed?
Bolded.
Yes, because everybody, you all see it's to your right. If I'm over here to the right, it would be bolded. And that means that the 1, 2, 3, the butyl group would be back. 1 carbon, 2 carbon, 3 carbon, 4. So we can maintain stereochemistry here. It's not important for nomenclature, but let's do it anyway. Back carbon. What's on the back carbon? What are the 3 groups on the back carbon? 2 H's and an F. There you go. You see the 2 H's there? 2 H's and an F. And we'll also learn, this is a chiral carbon, so stereochemistry is important. That's not chiral, so projections don't matter. All right, we'll have to learn when it matters.
So we learned that the largest like group number of carbons would be the one that's like mixed with it.
So name this compound. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Anyway, 6. What's the base? It looks like 6, but which 6? How do you break the tie if you got 2 6s?
Closest
Well, with most subs. If this is 6 through here, if that is 6, we got 2 subs. If this is 6, there are 3 subs. And that is it. There's that. So that's hexane. What is on the hexane? We got an F and 2 methyls. Where's the 1 position? This end or this end?
Right in.
1. Then this would be 2. 2, there's 2 methyls outside the parent. Okay, here's the name. 1 fluoro, 2, 2 dimethyl hexane, all one word.
Isn't that?
Is that not a bromine?
Our bromine?
Okay, we forgot the bromine. It's not 2 methyls. It is the front. This should have been bromine, right?
Yeah.
Okay. So it's not dimethyl. It's going to be a 2. It's not a di, it's a 2 methyl. B becomes before F, so 2 bromo. Someone say 2 butyl? No, 2 butyl. Two bromo, 1 fluoro, 2 methyl hexane. Yeah? Yep.
The B and the F should always have to be capitalized.
No, this, I would have only capitalized the front, the first one. Yeah. That's a minor point. Sorry, I didn't have the bromine there, and then we had to go readjust it. Okay, you can try one on your own. I gave you kind of the way to do it. We didn't have to worry about stereochemistry. During test 2, we'll want to maintain the stereochemistry and be able to name it. We'll put stereochemical descriptor in the front. Okay, cyclohexanes. We introduced cyclohexanes in the other handout. With the disubstituted ones there. We need to look at conformations of those type compounds. Just the 6-member ring. I have one here, it's smaller. Okay, 6-membered ring. Each carbon is tetrahedral. All right. group some here. Because of the tetrahedral nature, this thing is not flat. Okay? We'll draw it on the board flat. I mean, if we just draw a cyclohexane, we can do that. It looks flat on the board. Okay? We know each carbon has H's, but it's not flat on the board. That would be flat. 2 in the plane, 1 H forward, 1 H back. Every carbon is tetrahedral. Okay? But it's not flat. One reason it's not flat is if it was, look at neighboring H's. What are they doing? They're eclipsing. Okay? Look at them. Any neighboring H's, you see the two? They're eclipsing. Also, you see how my model is very much bending here? 9th grade geometry tells us that the angle in here is greater than 109.5. Okay? We can get better angles and we can avoid eclipsing by doing this. Let's move that up and this down. Now look at neighboring H's. There's one over there. See the one here? It's no longer eclipsing. Neighboring H's are now staggered. And the bond angle is better. Okay? See, my bond is not wanting to break anymore. So what we have is 4 are in the plane, 1 carbon's forward, 1 carbon's back. In the end, this is called a boat conformation. I'm sorry, not a boat. This is chair. Pictures are going to be better. We'll start drawing. Chair, you sit here, your feet spill over, and this is where you put your back. Okay? Now, we could have did this. Instead of 1 up, 1 down, we could have put both of them up. That's forward. Both carbons are that's in the plane, and both carbons are forward. That's called a boat. It's like an Italian gondola with the ends of the boat both up. Okay. This is not as good, and this will be the last time we ever show it. It's not as good because these 2 H's up here, they get up there and clash with each other, even though they're small. Okay. And thus, it's better to have one up and the other end down, and this will rotate. And that's called a chair conformation. Because now you can sit here and I can watch TV and my feet come back. Okay? And so we're going to learn how to draw chairs and there. And ring flip. Okay. Let's just get at the things we need to do here. Understanding axial versus equatorial. How do you draw this on the board? Okay, let's do that. Two offset lines, parallel, boom, boom. Okay. That there's 4 carbons. Connect that with 1 carbon. That's 5 carbon. And then connect this with a point, and there's your 6 carbons. And that's a chair conformation. So here's your back, the feet can spill over here. Okay, we need to draw in the H's here. It has what I call up carbons. These 2 and that one are up carbons. Up carbons get straight up bonds. Straight up, and these are all going to be H's. Straight up, straight up. The down carbons, the other 3, which they seem to be kind of down to you, hopefully they do. They get straight down bonds. And all of these are axial. called axial positions. The other H on each carbon is going to be equatorial. Equatorial is drawn parallel to another bond, not the one that's there connected to that carbon with the next one. So it's going to be here. And these two are parallel. This one here, parallel not to this one, but this one. And so these are parallel. This one, not that one, but this one. And these are supposed to be parallel. These are supposed to be parallel. These are supposed to be parallel. Or that. You can go 2 bonds away that way or 2 bonds away this way. And over here, not that one, but the next one, and it's here. And the black ones here are equatorial. You can see those here. Share conformation. Let me set it down. How many H's are hitting the table? Can anybody see? 3? 3. Those are the 3 H's that are straight down. 1, 2, and 3. Those are the ones hitting the table. There's also 3 straight up. If I flip it over, there'll be 3 hitting the table that way. That's 6 of the H's, up or down. The other H's would never hit the table. They're always going to be to the side, like the equator around the Earth. Okay? They're called equatorial. That is cyclohexane. We can do a ring flip. I don't think we have time to draw a ring flip. Let's try one of these over here. Understanding cis or trans. Okay? Cis or trans. Remember cis or trans on the previous page? Cis would be both, so it's the same. Okay? Are these two cis or trans?
Trans.
To answer this, you want to draw in the H here. That's a straight up H. This chlorine is equatorial. Bromine is equatorial. That's a down, that's a straight down. And to get this answer is, compared to the H, the bromine is up. Chlorine is down compared to the H. That's opposite. Those are trans. Those 2 halogens are trans. If we drew that in a more perspective drawing, it would look like what? Importantly, if that's 1, we call that 1. If that's 1, that's 4. Bromine here.
Opposite sides.
Does everybody agree that that's trans? Those are the same compound, drawn 2 different ways. Perspective drawing using dashed or bold. This would be drawn in a shared conformation. Because this looks flat on the board, it's not really flat on the board. Okay? I'll finish up here if you give me here. Bromine equatorial, chlorine is over here. Hopefully that's it on the board. Yeah? Both of these are equatorial, yeah? Chlorine blue. Alright. Let's put it up here. Let's make the ring flat. Not really in real life. And look at the 2 groups. Are they on the same side or opposite? On opposite. See, now it's more like this. I don't remember which is blue, it really doesn't matter here. But if bromine is forward, red forward, and chlorine is back. Okay? So we went from, that's kind of what we need to do. We need to be able to go back and forth here, understanding relative positioning, cis or trans, as we introduced on that other page, and try the others. Down below, we're going to say this ultimately. What's the best position, axial or equatorial? Equatorial is the best position. So if you're asked to draw the best chair conformation, you want to have your largest groups equatorial. We'll pick up here on Friday after our quiz. Have a good day, guys. If you want to come by the lab, I'll open it up as soon as I go up.